Go, start recording. Cool. All right, so many of you are going to find these 4 lessons boring and stuff that you already know. But it's important that everyone is up to speed. So this is going to be a quick little refresher of the kind of stuff that you learnt last year that you absolutely need this year. Okay? Yes?
Circuits?
No. It's more vectors and motion. So, I've got an ink to shape. What are you doing? I don't want ink to shape. Go away. All right, here we go. Oh, that's a nice straight line. All right, suppose we have a vector. Now, I will try to be consistent, and some books you will see that vectors have little accents above them. That means it's a vector quantity. So this could be speed. It has magnitude, and it also has direction, theta. We want to split. Yeah, here we go. There we go. See, look at that. There we go. Done. I've already screen captured this from the other lesson, but we'll see how we go. I'm also going to full screen this. There we go. We want to split our vector into its components, both horizontal and vertical. Can you see? Now, I have discovered that my screen capture software doesn't drop out like QuickTime used to. So that's a plus. I'm still going, yeah. Reconnecting. Hang on, it's telling me. It's also telling me that there's no internet. What's the code? 7321? And apparently, still recording. Isn't that lovely? Thanks, OBS. Unfortunately, that's not minimizing. All right. There we go. That's what I was trying to tell you 2.5 minutes ago. We want to split our vector into horizontal and vertical components. And in this case, we would say that that is u, oh, I forgot my hats already, u sine theta, and ux would be u cos theta. Now, do not rote learn sine is vertical and cos is horizontal, because sometimes you might not be given that angle to the horizontal. You might be given the other one. You might be given the angle to the vertical. So you've just got to use some quick SOHCAHTOA, because a question may give you the other angle. All right, so you don't want to have it the wrong way around. So if we could consider a cannon that fires a projectile at a speed of 30 meters per second and at an angle of 20 degrees to the horizontal, we can then split it into both horizontal and vertical components. So ux equals u cos theta, which is 30 cos 20, which is 28.2 meters per second right. 3 sig fig and all that. And then uy, forgotten all my hats already, equals u sine theta, (10.3 meters per second upwards. Now, some of you might already be aware of why we do that, because in projectile motion, the only force that's acting is downwards, and so the downwards only affects the upwards and downwards component of our vector, with ignoring air resistance, right? So ignoring air resistance, this is not affected because there's no force in the horizontal component, or in the horizontal direction. So that remains constant. Our vertical is changing by 9.80 meters per second every second downwards. And so we have to split it apart, figure out how the vertical's changed, and then recombine it at the end. Okay? But we will spend a lot more of that in week 2. Okay, so that is the component. We might also want to combine. And so the example I'm going to provide here is a helicopter might be able to travel with a speed, V helicopter, equal, let's just go back to black pen, equal to 20.0 meters per second, let's say east, but it happens to be pushed by a wind, the wind, that could be 11.0 meters per second north. And then the question becomes, at what speed with respect to land is this helicopter seen to be pushed? So we need to get both magnitude and direction. So this is quite a simple one. The magnitude of our velocity is simply Pythagoras, square root of 11 squared plus 20 squared, square root of 521, which is 22.8. And then our angle theta, arctan, opposite over adjacent. Now, I will generally always go, not always. In this scenario, we found a value, and we may have had to have rounded it to 3 significant figures. If we use this number down here, we could have used sine or cosine. That rounding could introduce a difference in that last figure. So to prevent that, always use, where possible, use the values given in the question. Okay? So then you don't have to round. So use 11 and 20. So you're going to use tan. Don't use 11 and 22.8. Don't use sine, because then you might get an error. Okay? And so we get an angle of 28.8 degrees. In most questions, you should be given some sense of direction, but always assign your conventions at the start. Now I'm going that up is positive, down is negative. Could you shut the door, please, Ben? This question could be sort of east and north, because we're going to bring in some direction now. We're going to combine our magnitude that our vector is 22.8 meters per second. Let's go east 28.8 degrees north. Okay. Now, just here is where I'm going to stop and suggest the term intermediate rounding Weiss or Scarza suggest that if you have intermediate calculations, to get an answer you might need to solve for A, then find B, and the answer requires C. They recommend that you round your intermediate steps to 3 significant figures, and the majority of their marking keys will show that. Okay? There have been a couple of contradictions that some very cluey Year 12 students in the past have brought the marking key forward and said, look, they've made a mistake. But round to 3 sig fig. Okay? But because you round in intermediate steps, there is now a button that you are no longer allowed to use. Do not ever use this button anymore. Okay? That's the memory button on your calculator. Do not just go answer equals. Okay? Do not use. Because what that memory recall button does is it keeps the entire value to 8 or 9 significant figures, and then it does the operation that you require it to do. Now here's the problem. 90% of the time there won't be an issue. But 10% of the time, you round this number to 28.8, and then you write 28.8 times 3 equals 90, blah, 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 blah. There's your answer. But if you wrote, if you go calculate it, answer times 3, it doesn't take 28.8. It takes 28.7643244 times that by 3. Now, 10% of the time, that might be a different number in that third significant figure. So you write down what the calculator shows, 93.4, but what you've written is now mathematically incorrect because maybe it's 93.5. And you've said that A plus B, or 1 plus 2 equals 4, if that makes sense. It's difficult to spot. And your teacher is not going to sit there with a calculator and do every single calculation to check your work. But if you've written down something that's mathematically incorrect, you could lose marks if you use. So don't use that. If you round, write it down and then re-enter it into the calculator. Clear your calculator and retype it. Think about it. It's a 3 significant figure number. It's not going to take long. Where you can get caught out is if a teacher was to mark, 46 test papers, and that teacher marks all of question 1, they get really, really good at looking at what the answer should be. So if the answer was 93.4 tick, 93.4 tick, 93.4 tick, 93.5, hang on, nah, that's wrong. Take a mark off. And then you bring your paper up the next week and go, oh, but I got it right. No, you didn't. You've written something down that's wrong. So think about that. Even with the exam, when I take section A, I'm going to be marking 70 section A's. And I'm going to mark all of page 1 first. Same with the waste markers. They get they mark 160 to 200 scripts. And so they find out very quickly. I'm not allowed to say that I am a waste marker. I'm not allowed to say that I will be marking waste. But when I was marking waste last year... Wait, am I allowed to say that? I think I can say that. When I was marking waste last year, I found 3 or 4 students, these poor students, they made an error. The answer was 93.4 and they'd written 78.2, but their working was correct, but the answer was wrong. So I got my calculator out and I set my calculator to radians. And outspat the number. This poor student sat the waste exam with their calculator in radians. Right? And there was, not only was there 3 or 4 students that I found, but in that waste exam last year, there was about 3 or 4 questions throughout the test that required degrees. So I left a note. You can leave a little note for the chief marker. So I flagged that test. I said, this poor soul has left their calculator in radians, and then they could look at the test as a whole and decide, well, do we take 5 marks off this student or do we take 1 mark off because they've only really made 1 mistake. So again, make sure, and I'll come back to this. There's a couple of little tricks that you can do as you go along to prevent you losing marks unnecessarily. Okay, so don't ever use the answer button. Now, this is like year 11 level, and I would dare to say that even the following is year 11 level. Let's crank it up a notch. Let's take our helicopter that can travel 20 meters per second in still air, but now let's give it a wind speed that's not at a right angle. Let's suppose that they travel 11 meters per second, and that wind is blowing 60 degrees. Can we read that nicely? 60 degrees to the east. East, 60 degrees north. Okay? And now the question becomes, well, what is the sum of those 2 vectors in magnitude and also direction? Okay? So this one's not too tricky. We've got an outside angle. All we need to do is find an internal angle. 120. Exactly. So we've got 20 here. We've got 11 there. This is where we use our angle along a straight. If the outside is 60, then the inside must be 120. And once we've got that, we've got the sine and the cosine rule to help us find magnitude and direction. Now, again, sine and cosine rule is not normally used in year 11, but most of you would have learnt it in either of the maths methods or apps. So we can say, again, the magnitude is the square root of a squared plus b squared minus 2ab cos c. All right. Before you rush to your calculator, in fact, you don't need to rush to your calculators because I've done all the calculations. But suppose you foolishly came from spec maths who are trying to scare you with radians and gradients, and your calculator is still in radians. And I don't know what the relative amount is, but let's say half the time this method will save you and half the time it won't. But let's have a look. If I've got these two vectors, 20 and 11, and I can add them and combine them in any possible way, what would the biggest sum be? Go, Marnie.
Just under 31.
I would say exactly 31.
Oh,
Put them in the same direction.
Oh,
yeah.
Yeah, the result.
If you just add that one and that one, it's 31. Now let's fold that back. 9. Yes. So the possible ranges of answers from 0 degrees through to 180 degrees is going to range from 9 to 31. Let's go a little bit further. Our hypotenuse in this diagram has to be greater than 20. So, between 20 and 31. Cool. So before you race to your calculator, you know you should be expecting a number between 20 and 31. So if your calculator spits out 12, that's not right. Something's wrong with your calculator. Or maybe you forgot, you put plus instead, or maybe you forgot to times it by 2. Sometimes you can get saved by little errors by going, all right, I'm thinking that it should be around 27.1 meters per second. Okay? Next, well, we're going to use sine theta on 11 is sine 120 on 27.1. And so theta, I'm going to do 2 steps here. I'm going to times both sides by 11 and then take the arc sine. Same deal. If you've got your calculator in radians, then you may get a completely whack answer. Let's use let's use our interior sum of a triangle. What should they add to? 180. Well, what should theta and phi add to? 60. Well, let's just share, let's say that plus that must add up to 60. Let's share it half-half. I'm expecting around about 30. So again, before you race off to your calculator, you should be thinking something in the 30 range. Well, in this case, it came out to be 20.6. Okay, which sounds plausible. So then we recombine V equals 27.1 meters per second east, 20.6 degrees north. Okay? Is that large enough for the boys at the back to read clearly? Yep. Okay. Now, next, this is taught, I believe, in Year 11 methods last year. And you've... Spec? Okay. Relative velocities. So if you had V of A relative to B, that's going to be VA take VB. Is that correct? Oh, wrong way.
Well, it says it's right. It's right. If you're taking the velocity of A relative to B,
then it is
B minus A.
A relative to B.
A relative to B is, VA takes VB.
Okay, which is what
Why is A relative to B?
Think about it, Joe.
well, we'll find out soon enough. All right. Okay, guys. We're back on track here. A take B. Does B take A? A take B. I could just cheat and look at it. All right. Now, we are going to be taking measurements in these. We're going to be taking measurements in these classes. We're going to be doing investigations, and at most times we are at rest with the apparatus. So, most cases, we're fine. We don't have to take relative velocities. But then they want you guys thinking about what if someone was taking a measurement and they were moving relative to you? Well, they would see the world slightly differently. So I'm going to give 3 different frames of reference. I'm going to have a person standing on the side of the road, stationary. That's nice because their motion is stationary. Let's say that we have a hoon, VH, that's hooning south at 20 meters per second. South. So, I don't know, they're heading towards Freo, going down Stirling Highway. And then you've got a granny that's travelling north at 10 meters per second. Okay? So now we've got 3 different frames of reference. Now, let's just check this equation. The person at rest, we don't really have to care about them. So we would say the velocity of gran relative to the person is going to be v gran take v person. Well, you're just going to take 0, right? So we would say he would see, from his frame of reference, he sees gran going 10 meters per second north. Same with the hoon, VH minus VP 20 negative, he sees negative 20. But now let's look at what does gran see? Well, the velocity of the hoon from the frame of reference of gran is going to be v hoon minus v gran. My laptop is starting to lag. I don't like that. Now, negative 20 minus plus 10. Now, it's important, gentlemen, that we keep all of the pluses and minuses. So that plus represents the north vector direction. This is going to be the subtraction of one vector from the other. Okay, so they have different meanings, but mathematically they're going to do the same thing. So this becomes negative 30, but we don't leave direction as pluses or minuses, so gran sees the hoon approaching her with a relative speed. Relative to her, she's stationary, even though she's moving, she's stationary, and she sees this car approaching her at 30 metres per second. You might wish to quickly check from the other frame of reference, the hoon. Obviously, the hoon's going to see the same rate, the same magnitude is 30, but he feels that he is stationary, and the gran is approaching him or her, hoon, generally men, 30 metres per second north. Okay? And there was a head-on collision that was in the news recently about a police officer that recently lost his life. They said that the relative speed of impact was 200 kilometres per hour because the rural road they were on had a speed limit of 100k an hour. So when they crashed, that's a relative impact or a relative collision of 200.
Hitting a stationary car at 200.
Or like hitting a stationary car at 200, it's going to have the same amount of energy. Okay, so you can look at relativity in a lot of different topics in physics. We will cover relativity when we do Einstein and special relativity because weird stuff happens when you go really fast. But I just thought we would cover that quickly. It is needed this year, but not until a bit later. Okay? How are we going for time? We've got 15 minutes. Where is the rest of my working out? Okay. I'll give you a collision question. Why is my laptop lagging like this? I just want to check something. Give us a second. My CPU is running at 9%. Now it's down to 5. Do you think it overheats if the screen's down? Do I need to leave it open so it can breathe?
I reckon it's the network's just not.
So the Wi-Fi.
Okay. So, gentlemen, next topic. Now, suppose we had a ball that's travelling and it's going to strike a wall with a certain speed u at a certain angle theta, and then it travels off with a speed v and let's say the same angle. Now, this is obviously an elastic collision. Well, in fact, the only way we can show that's elastic is if they have the same energy, which means that the magnitude of v equals the magnitude of u. This is not a realistic scenario. This can occur only with sort of charged particles in vacuums or planets traveling around other large masses. But if a ball struck a wall, it's going to lose energy. There's going to be some frictional forces going on. But what we want in this is to look at the change in velocity, which is v final minus v initial, which is v take u. That's a vector subtraction. Now, you may have covered this in year 11, but this is revision, so we're going to go through it again. That can be written as v add negative u. Okay, put all these hats on, doesn't really matter. Now, what I've got drawn there is u, so what I'm going to draw is negative u. Negative u is the same magnitude but in the opposite direction. Negative u. Okay? And so that theta, it's the same angle but pointing backwards. So now if I was to draw delta v graphically, you would have v add negative u. And so now our delta v would look like so. Now I haven't, if that's theta, and then that's phi, and then that's going to be 2 theta, up there would be phi, that's equal and that's equal. It just becomes an isosceles triangle. If I made it 45, if it came in at 45, then boom, that's 90 degrees. And it's a right angle triangle. But that's just for 45. I could make it 60 and 60, in which case this becomes 120. We're not going to do any workings because that's too easy. And in fact, if you're happy to, you could treat this as u and u, or v and v. You, the smart cookies in this class, should be able to prove that delta v is always perpendicular to the wall that it strikes. We cannot say right now that that's going to be a right angle, even though we know it is. You could use some geometric proofs to show that that plus that equals 90. There's probably going to be a couple of trig identities that's in your maths data booklet that you can use to show that delta v is at right angles. Okay, let's have a look at a more realistic example. So this is more realistic, and that is when v is less than u, meaning it slows down. It's going to lose kinetic energy as it strikes. Okay, so let's do a worked example. Let's suppose that the object comes in with a speed of 5 meters per second. Oh dear, 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 dear. Oh, hang on. Let's have a shape. Yeah. I got to start. Oh, that's too low. Can I move it up? No.
It's a bit of a bra moment.
Oh. This is, and then, nah, I'm not doing this. I'm going to be here forever. And then it bounces off. Now I'm going to change the angle. Let's put the angle in. Let's say that it struck at 50 degrees. And then it bounces off with less speed. So let's say 4 meters per second. And it recoils backwards a little bit at 55. Okay? Now, and that's u, and this is v. Okay? Now, if u is 5 meters in that direction, I'm just going to very quickly over here, I'm going to sketch negative u. Because to draw the vector diagram of delta v, we're going to add that to okay. So here we go. Here's V. And then here is negative U. And then here is our delta V. Now I've exaggerated this slightly, but I know that if we've reduced the horizontal component and increased the angle, then your change has to be backwards. It's still out from the wall, which I could sketch down here, but it's backwards. Now, with our U value, we're going to zoom in here. We have two known values, the two side lengths. We need to get one internal angle. And this is again where we need to draw in our little rule. So if I know that this is 55, I could draw in the alternate angle to the horizontal is 55. And oh, this was easy. Look, I know that U to the horizontal was 50. So hey presto, I now have my internal angle as 105 degrees. So this one actually wasn't too difficult. You just had to remember your rules that they teach you in Year 9 mathematics about co-interior, supplementary, complementary, triangles, alternating, parallel, all that stuff, because it has applications when you're looking at displacement and velocity vector addition or subtraction. Okay, so we will now use our cosine rule to find the magnitude of delta V. And that's going to be, zoom out a little bit, Barty. There we go. Square root. I've forgotten the values, so it's a squared plus b squared minus 2ab cos 120. Yes. Well done, you passed my first test. Now, again, remember what are we expecting it to be? Greater than, less than?
Less than 9.
Less than 9, yes.
Greater than 1. Greater than 1.
Or yes, but I would say greater than 5 because our hypotenuse is the longer of the two. That's 5, that's 4, so it's definitely greater than 5. So between 5 and 9, calculator spits out 7.17 meters per second. Okay. How are we going for time? Thank you. Sine rule. Again, we have to use a calculated and rounded number because we have too many unknowns. But what we're going to do is find, let's call this bad boy phi. Okay, so sine phi on 5 equals sine 105 on 7.17. I'm going to do 2 steps at the same time because I'm lazy. I'm going to times both sides by 5 and then take the arc sine. Quick little practice here. I'm going to put up here alpha and phi. What are we expecting phi to be less than, greater than?
It's going to be less than 75 degrees.
Correct. Probably greater than 0, but again, I haven't drawn this to scale, but let's just share that 75 equally. We're aiming for about 35-ish. Calculator says 42.2. Oh,
God, someone pressed ants.
I didn't press answer.
what'd you get? 42.3.
Yes, sir.
Risky. Now, this is the angle between the final velocity and the change in the velocity. So you're not going to express the change that way from the final. We want it with respect to the bumper or north, south, east, west, or up, down, left, right. So I would suggest that now we know theta. Let's find beta. Okay, and we could say that beta equals 180 less 42.3 less 55, and we get, I believe, 82.7. I think. Okay. So just finishing on this, you've got 2 different ways. That's east 82 degrees 0.7 north, or right 82.7 degrees away from the bumper or the wall. Let's go. Or you could take the complement. So you could go from the normal and then bring it back by 7.3. But so we'll just leave it like that. That's fine. Okay, they will accept either. You don't have to take the simpler angle. That's fine enough. Okay. Just in the last 2 minutes, I need to do attendance, but I also want to show you in the OneNote. So guys, when you click on the OneNote link, you'll be opening it in a web browser, and you'll have the same tabs here. So the Working in Physics tab is the Year 11 topic you would have learned in week 1 of last year. That's all your sig figs and your combination of uncertainties. All right, you would have gotten this booklet right at the start of Year 11. Okay, and I've left. These are the lessons that you might have been in from last year, and some important links. The first tab is the programs and documents. That's got your course overview, your assessments, the data sheet, any useful course documents. You've received the hard copies, but they are also available on Nexus. They are also available on the OneNote. I've added some incredibly useful websites, and I'm going to continue to add to these. So these are some cool physics websites that might assist you. I'm starting to make very short tutorials on how to make tables, nice looking tables in Excel, how to use motion capture software, software that's available for you to download from Software Center. Just before you depart, the Jan Coley textbooks. We've got the 3rd edition off on the shelves there, but I've got the 6th edition. It was one of the textbooks at Murdoch University's 2nd semester Year 1 physics, and I've scanned some relevant chapters. Okay, and there are plenty of questions for you to attempt. So I'll be giving you guys homework, and it'll be to complete the Nelson chapter questions 1 through 10. And you might do them like that, and they're freaking easy, done. Okay? You have to do that first. If I'm citing homework, I need to see it. If you want to be challenged, there are these Jancoli questions which you can access. And the great thing about this is they start off level 1 difficulty. Very, very simple. Stuff that Year 11s could do, Year 10s could do. A car drives west and southwest. What's the displacement? Draw a diagram. Done. You'd have to assume 45 degrees. Oh, look, that's just a scaling triangle. Cosine rule for magnitude, sine rule for angle. Easy. I could put that question 1 of the test. Right? Number 2, starting to get a little bit trickier. Level difficulty 2, that's kind of the extension question. Maybe I could put one of those nasty questions in the test as the differentiator or the discriminator. And then there are level 3 type questions, which are way beyond, like, they're crazy difficult. And I'd have to sort of sit down and think long and hard about how I would approach this. This would be university level physics. But if you want to push yourselves, if you want some nasty, tricky questions that as I said, that extend you to your abilities because you're finding the Year 12 questions too easy, have a go. Okay? So they are there, and I showed some of the boys, in the last week of last year, we had boys doing level 2 questions up on the whiteboard and other students on the other side, working together and trying to figure out the answers to some of these tricky problems. Okay? So I just thought I'd show you that. But basically the OneNote and the course page, that's where you find everything. All right? If you've got any questions, feel free to ask.